Let's take a look at problem 103 here. It says find the volume of the solid under the plane z equals 3x plus y and above the region determined by y equals x to the 7th and y equals x in quadrant 1. So the first thing I want to do here is try to understand where my region is, specifically for the sake of the bounds of this double integral. So what we're going to do first is we're going to graph it and determine where these bounds will be. So now taking a look at the y equals x to the 7th, we're going to graph that first. So we're just going to plot some points. So when I plug in 0 for x, I get 0 for y. When I plug in 1 for x, I get 1 for y. And that's when I plug in -1 for x, I get -1 for y. So those are 3 points we see right away. Now another thing to notice here is when I actually plug a 2 in there, I'm looking at 2 to the 7th, and that's 128. So this thing, when it gets to 2, shoots really high. So I'm not going to plot that. It just gives me an idea of how this thing is working. And notice when I do a 1/2, so that would be here, that's going to give me a 1 over 128. So that's going to be almost at 0. So at the 1/2, it's going to be way down here. Let me try to straighten it out a little bit more. Okay, that's a little better. But very close to the x-axis. And then on the other side here, at -1/2, I'm going to get a -1 over 128, which is very close to 0. So I'm just going to try to keep it this way. I want to keep it somewhat true because when we set our bounds up for this, we want to make sure it's clear where those bounds will be. Now, when I graph this thing, and like I said, when I get to 2 here, that thing's all the way up to 128. So this thing just skyrockets. So now, drawing my lines. Oops, I'm not going to go as high. I don't have to. Okay, so that's kind of what I'm looking at here. Okay, now I'm going to go the other way as well. And that would be the first graph there. I missed that other point, but I'll leave it. Doesn't matter. You guys understand. Just make it bigger. So anyways, now I'm going to draw the other equation. Now that other equation is y equals x. So now when I draw a line there, there it is. Pretty good line I drew. All right, so anyways, so now the region of interest would be here. Now those two bounds actually enclose that region, and keep in mind here, this is also in the first quadrant. If I didn't say in the first quadrant there, we would also be including this. But because I said that, this is our only region right here that we have to consider. Now what we're going to do is we're going to talk about how to set this up. This is why it's so important to have a picture of what we're dealing with here so that we can determine which functions on top, the upper bound, lower bound, all of those components come into play here. So what I'm going to do now is we're going to just talk about which one should come first. But before I do that, I guess, not first, then second. So the first thing we're going to do is find those points of intersection. So we're going to need to know where this is at here and this is here. And by the graph, since I did such an awesome job, kidding, we can see what it should be. And we're probably right. So again, when I have a system of equations, a nonlinear system of equations, I use substitution. And in general, you can say, hey, I can use substitution all the time. So this one says y equals x. So that means for every y, I can just plug in an x for it. And that's what I'm going to do. I'm just going to plug in an x there. So this is going to turn out to be x equals x to the 7th. Now, keep in mind here, I can't divide by x. That's illegal. Don't do that. So the only thing I have here is factoring. So I can move that over. So I'm going to move this x over to this side because I like to leave the leading coefficient positive just so I don't have to do negative signs unnecessarily. So I'm going to subtract x. So this is going to be x to the 7th minus x equals 0. Okay, now from here I can factor an x out. And then I have x to the 6th minus 1 equals 0. So that tells me then that x equals 0. Or x to the 6th minus 1 equals 0. Now we're going to, this first equation is solved, so now we're going to solve this equation here. Oops, I'll leave that there because that's one of my answers. So the x to the 6th minus 1 equals 0. I'm going to move the 1 over. That's x to the 6th equals 1. I'm going to 6th root both sides. And because this is an even index here, this follows the same principles as x squared, or I should say square root of x. So then these are going to cancel. I'm going to get an x, and this is going to equal plus or minus 1. Because 6 times 6 times 6, 6 times, or I should say 1 times 6 times 6 times 6, 6 times is going to give me 1. So the 6th root of 1 is 1. That's the idea. So I get these two answers here, which makes sense. I should get 3 answers altogether. And I'm going to separate these so that you can see them all physically here and from the graph. So we got the 0, and the 0's here. The x is negative 1, so that would be here, which would mean I'm looking at that point. And then the positive 1 is here, and that means I'm looking at that point right there. So that's the idea of what we're dealing with. So it makes sense what we have. Now, the other nice thing about this, since one of my equations is y equals x, that makes finding these points very easy because it doesn't matter what function I plug it into. So now when x is 0, and I'm going to take this one up here first, I'm going to get 0, 0 because x is equal to y. And then I'm also going to get negative 1, negative 1. And then my last point is going to be 1, 1. And it's only because of y equals x here. So those are our 3 points of interest here. So I could label those if I want to. And 1 and 1. So now what we're talking about here is, since we're talking about that green region here, right in here, then we're talking about using these 2 points here. Now, from those points, we'll determine what our bounds and everything are going to be here for this problem. So that's what we're going to do now. So I'm going to get rid of this other information when we get started. So now when setting up this double integral, I'm just going to put the integral symbols in, and I can put the z in here, which is my fxy, technically. Now this is where I have to determine if I'm going to do dx or dy. Now this one I can actually go both ways, but I'm going to explain my rationale for even picking a method in which to do this. So what I look at is there a clear upper and lower function for these? So what I mean by that is when I go from 0, and I always look in the x direction first. Let me pick a brighter color. So when I go from 0 to 1 here, oops, I went too far. When I go from 0 to 1 here, do I have a clear upper and lower function on the x? Then if I don't, that's when I switch to the other one, the y-axis. And those are my only 2 choices here. So when I go from 0 to 1 in the x direction, do I have a clear upper function? The entire interval, and I do. I have this one here. That one's always going to be above the red one, which is y equals x to the 7th. So since that one's always above it, that means I can go in this direction. Now I'm going to write these equations out on the actual picture because I want you to see this. So we can see that our lower bound for this is going to be x to the 7th, hopefully. Now again, notice what's really going on here. I'm talking about this change here. And that's what's going to give us our area, is that change. So that change is in the y direction. So we're actually looking at a dy. And that makes sense now that these would be functions of x. So that would be x to the 7th, and let me do the right color here. That would be x. Now I'm asking on what interval, because my next idea is the dx here. So now that's our change in x. So where's our change in x at here? And our change in x is from 0 here to 1. That's going to be our change in x. So that's going to be from 0 to 1. So now we're all set up to do our integral here. But again, it always comes back to the idea of understanding the picture that you see here and being able to determine if the function is on top on the whole interval on the x or on the whole interval of the y. And that determines what I do first. So the integral then is going to be from 0 to 1. And I'm wondering, no, this will be okay. All right, so we're going to go with 3. Well, since it's with dy first, that means 3x is a constant. So that's going to be 3xy plus 1/2 y squared. And I got to put my bounds in here from x to the 7 to x. And then I still have the dx I'm going to have to do after that one. All right, so now I'm going to do my upper bound minus my lower bound here. Okay, so it's the integral from 0 to 1. And that's going to end up being 3x squared when I plug in the x here for y. And then when I plug in the x for y here, that's going to be plus 1/2 x. Oops, let me fix my x there. Almost looks like a y. X squared. Now I'm going to have to subtract the lower bound. Now I'm going to plug in x to the 7th in for my y's here. So I'm going to get 3x to the 8th plus 1/2 x to the 14th. Because remember, I'm plugging it in there and I got to square x to the 7th. That's going to give me x to the 14th. And we're still going to have dx to do. Okay, the next step, still 0 to 1. Now all I'm going to do is clean this up some. And these I can put together. 3x squared plus 1/2 x squared is 7/2 x squared. And then I have this minus 3x to the 8th and minus 1/2 x to the 14th because I have to distribute that minus through. And that's going to be dx. So now we're going to actually integrate these. More polynomials, so these aren't too bad. They just take a little while sometimes. Since we're dealing with ones and zeros, though, makes it very nice for us. All right, so remember, this is going to be a third now, and x to the third when I integrate it. So that means I got to account for it in the bottom here. So that's going to be 7/6 x to the third. Hopefully that's okay with you. If not, get a hold of me. All right, and then that 8th is going to become a 9th. So it's going to be 1/3 x to the 9th. And then this is going to be a minus 1/30 x to the 15th. And that's going to run from 0 to 1. Now, one nice thing about this, when I subtract my lower bound, I'm going to get all zeros. So that's going to be pretty quick. So now, first off, I'm going to plug in the ones here. And as you can see, it's not going to change the constants here, the coefficients, I should say. So this is going to end up being 7/6 minus 1/3 minus 1/30th. And then minus the lower bound, which is all going to be 0. Because I'm just plugging in 0 for each of those x's. And it's times those coefficients, so they're all going to end up being 0 minus 0 minus 0. So I'm just going to write minus 0 there to save a little bit of space here. So now then our final answer being, so just adding those together, same denominators, 24/30th, which reduces down to 4/5. So there's our answer for this one. So like I said, a big deal here is understanding the region. We're actually projecting up to the surface of the fxy function. So that's the big deal here. So we have to understand that in order to deal with our bounds. And if we're going to do a dy first or a dx first.